Hello viewers, I am Dr. Mala Das Sharma. Welcome you to my channel Chemphilic. Let's start episode number 53 of Teaching Chemistry through Riddle. Here is our riddle number 53. X is a theoretical tool for predicting aromatic and anti-aromaticity. It relies on the stability of molecular orbital as well as their filling by pi electrons. According to X, presence or absence of unpaired pi electron in the molecular orbital is the key factor for the compound being aromatic or anti-aromatic. So this is riddle number 53. Now let's see what is X. So the question is, what is X? Answer is Frost circle. Now let's discuss about Frost circle with respect to the following points. First point, silent features of Frost circle. Second point, method involved in Frost circle. Third point, correlation between Frost circle and Hückel's rule. Fourth point, prediction of aromatic and anti-aromatic nature of the compounds by using Frost circle. Now, the first point, let's see, that is silent features of Frost circle. It indicates aromatic or anti-aromaticity. It relies on the stability of molecular orbital. Bonding molecular orbitals are the lowest in energy, that is most stable, followed by non-bonding and anti-bonding orbitals. More electrons in the bonding molecular orbital means more stability. Less electron occupation in the non-bonding or anti-bonding orbitals means more stability of the molecule. Aromaticity is achieved when all the bonding orbitals are filled with paired pi electrons, while no unpaired electrons are present in the non-bonding and anti-bonding orbitals. Unpaired electrons, even in the bonding orbitals, often indicates an anti-aromatic compounds. Now, let's see with examples. Now, method involved in Frost circle or how to draw Frost circle. The first step is you have to draw the polygon in such a way, so it is hexagon, pentagon, whatever it is, in such a way that one vertex must be down. That means you have to cyclohexane, you have to draw like this. It should not be like this. This is wrong. So one vertex should be down. Next step, you have to draw a circle which should touch all the vertices of the polygon. Now, next step, you have to draw a line at the center of the circle, that is known as the central line. Next step, now the points where this circle is touching the vertices of the polygon, you have to mark it with lines. And these lines, that means the point of intersection of the circle and the vertices of the polygon, that indicates the molecular orbital. These molecular orbital which are below the central lines are known as bonding molecular orbital. And molecular orbital, if it is along the central line, so if along the central line, if any molecular orbital is there, then those molecular orbitals are known as the non-bonding molecular orbitals. And the molecular orbitals which are above the central lines, that means point of intersection of the circle and the vertices are above the central line, those points indicates the anti-bonding molecular orbital. And one more point to remember, that total number of molecular orbital formed must be equal to the number of vertices of the polygon. And it is true for any molecule applicable to study with the Frost circle method. Now, coming to benzene. We all know benzene is aromatic. It it is planar, cyclic, it has conjugated pi electron system. How many pi electron? 2, 4, 6. Now this is the molecular orbital diagram from the Frost circle. Okay, so 6 pi electrons. The molecular orbitals will be filled up from the lowest molecular orbital, filled up by the electrons starting from the lowest molecular orbital, and then it will go to that means electrons will go to the higher energy molecular orbital. Lowest molecular orbital means lowest energy molecular orbital. So there are 6 electrons. So 2 electrons will go to the lowest energy bonding molecular orbital because these 3 are bonding molecular orbital. Remaining are 4 electrons. Those 4 electrons will go to these 2 bonding molecular orbitals which are little higher energy compared to this lowest one. And see, number of electrons in all 3 bonding molecular orbitals are 2, 2. That means they are paired up. So this is aromatic. From Frost circle also we can conclude this is aromatic because number of electrons present in each bonding molecular orbitals are paired up, and there is no unpaired electron even in the non-bonding or anti-bonding molecular orbital. So aromaticity is achieved when all the bonding molecular orbitals are filled with paired pi electrons and no unpaired electron present in non-bonding or anti-bonding molecular orbital. Even if unpaired electron present in the bonding molecular orbital, that also very often indicates the anti-aromatic compound because unpaired electron means that is radical nature. These are very active, highly reactive, that is most unstable. But aromatic compounds are stable. Now, next see this one, cyclobutadiene. Okay, this is also they satisfying all 3 conditions, cyclic, planar and conjugation. There are how many pi electrons? 4 pi electrons. And when we draw this Frost circle, we get this how many molecular orbital? 1, 2, 3, 4. That is 1 bonding molecular orbital, 1 anti-bonding molecular orbital, and there are 2 non-bonding molecular orbital. So 2 electrons will go to the lowest energy bonding molecular orbital. Now remaining 2 will go to the non-bonding orbital according to Hund's rule. Okay, that means electron first it will be unpaired state, then pairing will start. So 2 electron means these 2 electrons will be unpaired in each non-bonding molecular orbital. So 2 unpaired electron means it is highly unstable, so it is anti-aromatic. 2 electrons in the non-bonding molecular orbitals are unpaired because it is filled up according to Hund's rule, which makes it highly reactive or unstable radical, diradical. Now, correlation between Frost circle and Hückel's rule. First, here you have to remember there is always an odd number of bonding molecular orbitals. Okay. Now, what is Hückel's rule? Aromatic compound must contain 4n plus 2 pi electrons, where n is the integer. Okay. Now, these 2 electrons, it will go to the lowest energy molecular orbital always. Okay. Now, if you exclude this molecular orbital or if you exclude these 2 electrons, how many leftover electrons? That is 4n pi electrons. N is the integer. So if n is 1, then it will be 4 pi electrons. N is how many bonding molecular orbital will be there? Number of bonding molecular orbital, remaining bonding molecular orbital will be even because as I told you, always it will be odd number of bonding molecular orbital. This lowest one is excluded. These 2 electrons have gone here. So remaining bonding molecular orbital will be even number and number of pi electrons also even number. So the other molecular orbitals will be filled up by even number of electrons. That means electrons will be paired. So when electrons are paired in the bonding molecular orbital, then according to this Frost circle, that is aromatic. And according to Hund's rule also, 4n plus 2 pi electrons means it is aromatic. And we have explained how it is 4n plus 2. 2 electrons in the lowest energy molecular orbital, remaining paired condition to the other even number of bonding molecular orbital. So it is benzene. Benzene is aromatic. Okay. Now coming to the cyclobutadiene, which has 4 pi electrons. Okay. Now from these 4 pi electrons means it is 4n, indicated by 4n number of pi electrons, that is anti-aromatic, we know. See, from this 4 into 1, if n is equal to 1, that is 4. Out of 4, 2 electrons are here. Okay, and remaining 2 electrons will go to the non-bonding orbital and they are unpaired state because it will be filled up according to Hund's rule. So as these non-bonding orbitals contain unpaired electron, so this molecule is highly unstable because they have radical nature, and this cyclobutadiene is anti-aromatic. Now, cross circle for 3-membered rings. See this one. This is cyclopropene. Okay. Now, this cyclopropene, there is no conjugation because this is not exactly sp2 hybridization. This carbon atom is not sp2 hybridized. So, no question of conjugation, only one double bond. So, cross circle is not applicable here. Now, we'll see this one. See, this is cyclopropene and this is cyclopropenyl cation. When this is cyclopropenyl cation, then this conjugation is present. Okay. See, this double bond positive charge separated by single bond. Conjugation is present. And how many pi electrons are there? 2 pi electrons are there. Now, when you are drawing this Frost circle, we get 1 bonding molecular orbital down and 2 antibonding molecular orbital which are above this central line. These 2 are antibonding molecular orbital. Then how many pi electrons? 2 pi electrons. So, these 2 pi electrons will occupy this bonding molecular orbital or lowest energy molecular orbital, and there is no unpaired electron in the non-bonding antibonding orbital, so it is aromatic. Now, Frost circle for 5-membered rings. See this one. This is cyclopentadienyl cation. When you draw this Frost circle, then there are 5 vertices, that means 5 molecular orbital will be formed, and out of 5 you see this 1, 2, 3. These are bonding molecular orbital which are below this central line, and there are 2 anti-bonding molecular orbitals. Now, how many pi electrons are there? 2 plus 2, 4 pi electrons. How these 4 pi electrons will fill up this bonding molecular orbital? 2 will go to the lowest energy bonding molecular orbital, and remaining 2 will go to these 2 bonding molecular orbital which are of same energy. So it will be filled up according to Hund's rule. That means 1 electron will occupy this 1 bonding molecular orbital. So this unpaired electron is present even in the bonding molecular orbital. So it is unstable because it has diradical character. It is unstable, so it is anti-aromatic. Now, when you come to cyclopentadienyl anion, then number of pi electrons becomes 6. 6 means it will go to this 3 bonding molecular orbital, and each bonding molecular orbital will contain a pair of electrons. So completely paired electrons in all the bonding molecular orbitals. So it is aromatic, that means stable. Next, Frost circle for Pyrrole and Furan. In Pyrrole, this is 5-membered ring. Here we know that this lone pair of electron of nitrogen is present in the p orbital, and that p orbital with lone pair of electron takes part in conjugation with this p orbital of all these carbon atoms. So delocalized pi electrons or pi electron cloud is present. So it is aromatic, we know. Now, how many electrons are there? Pi electrons? 2, 4, 6. Okay. Now, there are 5 vertices. 5 vertices means how many molecular orbital will be formed? 5. We see here this bonding molecular orbital, it has lowest energy, then other two bonding molecular orbital, and there are two anti-bonding molecular orbital. So 6 out of 6 electrons, 2 electrons will go to the lowest energy bonding molecular orbital, and remaining 4 will go to the other two bonding molecular orbital, which are a little bit higher energy, and that will be paired up. So all these bonding molecular orbitals are filled with paired electrons. So it is aromatic. Pyrrole is aromatic. Similar things with furan. In furan also, p orbital contains, it is sp2 hybridized like nitrogen here. Here oxygen sp2 hybridized, and p orbital contains the lone pair of electron and another lone pair present in the sp2 hybrid orbital. So here also 6 electron, 2, 4, 6 is one pair of electrons. And this Frost circle diagram also same. So 6 electrons will occupy the 3 bonding orbitals, and everywhere electrons are paired. So it is aromatic. Next, Frost circle for 6-membered rings. See here, this is pyridine. In pyridine, like all the carbon atoms of the ring, nitrogen also sp2 hybridized, and this lone pair is present in the sp2 hybrid orbital, and the p orbital of nitrogen contain 1 electron. So it takes part in conjugation with the p orbitals of this carbon. So it is fully conjugated. Now, how many pi electrons are there? 2, 4 and 6. Not this one. This is present in sp2 hybrid orbital. So 6 vertices. 6 vertices means 6 molecular orbital. You see 3 are bonding molecular orbital and 3 are anti-bonding molecular orbital, and 6 pi electrons. The 6 pi electrons will occupy the 3 bonding molecular orbital, and everywhere it will be paired up. So it is aromatic and stable. Now coming to pyrimidine. In pyrimidine also, these 2 nitrogen atoms, this p orbital of 2 nitrogen atom containing one electron like carbon atom, and this p orbital with 1 electron. Similarly for this nitrogen also, p orbital with 1 electron takes part in conjugation with the p orbitals of carbon, and we get the delocalized pi electron cloud. How many pi electrons? 2, 4, 6. Same like pyridine. And then here also, this is 6-membered ring. That means there are 6 molecular orbital, 3 bonding, 3 anti-bonding. 6 electrons will occupy these 3 bonding molecular orbital, and they will be paired. So it is also aromatic. Now, Frost circle for 7-membered rings. See this one. This is propylium ion, that is cycloheptatrienyl cation. There are 7 vertices. Okay. 7 vertices means 7 molecular orbitals will be formed. Look at here. How many are there? These 3 bonding molecular orbital, which is below the central line, and 1, 2, 3, 4. These 4 anti-bonding molecular orbitals which are above this central line. Now, how many pi electrons are there? 2, 4, 6. It is already cyclic, planar, because all the carbon atoms are sp2 hybridized, and this vacant p orbital, it takes part in conjugation with this other p orbitals of other carbon atoms, so fully conjugated. Pi electrons 2, 4, 6. So these 6 pi electrons will occupy these 6 bonding molecular orbitals, and they will be completely paired up. So propylium ion is aromatic and stable. Now, Frost circle for 8-membered rings. See, this is cyclooctatetraene. This is dication, and this is diana. So look at here. Here also there are 8 carbon atoms. That means number of vertices 8. Number of vertices 8 means number of molecular orbital formed also will be 8. So 2, this is 1, 2, 3. These 3 are bonding molecular orbital, and along this central line, these 2 are non-bonding molecular orbital, and these above 3 are anti-bonding molecular orbital. And when there is no electron in this p orbital of this carbon and this carbon. This is positively charged, and then these two p orbitals take part in conjugation with the p orbitals of other carbon atom which has 1 electron. So it is fully conjugated. Now number of pi electrons 6. These 6 pi electrons will go to the 3 bonding molecular orbital, and everywhere it will be paired. So this is aromatic. Now when it is dianion, then this p orbitals of this carbon contains a pair of electron, even p orbital of this carbon contains a pair of electron, and it will be fully conjugated. All these p orbital overlap both the direction and form the delocalized pi electron clouds. Number of pi electrons 2, 4, 6, then 8 and then 10. So how it will be filled up? Bonding molecular orbitals are 3. So there will be 6 electrons, pi electrons in the bonding molecular orbital, and another 4 will go to these non-bonding molecular orbitals, and everywhere electrons are paired up. So it is aromatic. Interestingly, both dication and dianion compounds have been synthesized and confirmed to have aromatic character. Now, is Frost circle an ultimate indicator for aromaticity? Let's see. See this compound. Cyclooctatetraene. Okay. There are 8 vertices, just now we have seen, and there will be 8 molecular orbitals according to Frost circle. 3 bonding, 2 non-bonding, and here 3 anti-bonding. Now look at here. When these, then how many pi electrons are there? It is fully conjugated. How many pi electrons? 2, 4, 6, 8. So we have to accommodate 8 electrons in the molecular orbital. So 6 electrons will go to the bonding molecular orbitals, and everywhere it will be paired up. Remaining 2 electrons will go to the non-bonding molecular orbitals, and there it will be unpaired. So there are 2 unpaired electrons in the non-bonding molecular orbital. So as per this Frost circle, this molecule is anti-aromatic. It should be anti-aromatic. But if there is a possibility of change the hybridization by the molecule or change the geometry, then it will do it to get rid of this instability or anti-aromaticity. So what happens? This cyclooctatetraene, it changes its geometry. It becomes like this. Now, in this geometry, the p orbitals of adjacent double bonds cannot overlap. It is just like that separate alkene. So it becomes non-aromatic. Though according to Frost circle rule, it should be anti-aromatic, but it changes its geometry and becomes non-aromatic, so that it can get rid of maximum instability. Non-aromatic means it will be more stable than anti-aromatic. Now, see, Frost circle for azepine and oxypine. This azepine, how many carbon atoms? 1, 2, 3, 4, 5, 6, 7. This is 7-membered ring. Okay. Now, 7-membered ring. Then how many pi electrons? Here, look at here. 2, 4, 6, and these 2 lone pair of electrons. That means total 8. Now these 8 pi electrons, how can you accommodate in this molecular orbital? Now if you draw the molecular orbitals, then there will be, how many molecular orbitals will be there? 1, 2, 3, 4, 5, 6, 7. Okay. So number of molecular orbital also 7. Okay. Number of molecular orbitals 7. And then how many pi electrons? 2, 4, 6, then this is 8. This is 8. So we have to accommodate these 8 pi electrons in the molecular orbital. 6 will go to the 3 bonding molecular orbital. Remaining 2 will go to this anti-bonding molecular orbital, and they will be unpaired. Okay. And here, oxypine also the same things. How many pi electrons? 2, 4, 6 and 8. Out of 8, 6 electrons will go to the bonding molecular orbital, and 2 will go to this anti-bonding molecular orbital, 2 anti-bonding molecular orbital, and they will be unpaired. So, when unpaired electrons are there in this antibonding molecular orbital, then what we can expect? It is anti-aromatic. But it's predicted anti-aromatic. But if nitrogen and oxygen were sp2 hybridized, here we consider nitrogen and oxygen sp2 hybridized. However, if they adopt sp3 hybridization, and they can avoid the anti-aromaticity and they can become the non-aromatic, slightly more stable compared to anti-aromatic compound. Okay. Now see this one. The cyclopropynyl anion. How many pi electrons? 2, 4. 4. So, and there are 3 vertices. So, 3 molecular orbital. Here you see 1 bonding molecular orbital and 2 antibonding molecular orbital. 4 pi electrons out of 4, 2 will go to the lowest energy bonding molecular orbital, and remaining 2 will go to the 2 antibonding molecular orbital, and they will be unpaired. So it is predicted to be anti-aromatic. But it may change the hybridization. That means it may change the hybridization from sp2 to sp3, and it can become non-aromatic. So from Frost circle, what we have seen that if the paired electrons are present in the bonding molecular orbitals, then the compound is aromatic. If unpaired electrons present in the non-bonding or anti-bonding molecular orbital, then they are anti-aromatic. Even if the unpaired electron present in the bonding molecular orbital, then also they can become anti-aromatic. Okay, so this is all discussion all about this Frost circle. Thank you.